In this video, we're going to look at Snell's Law. So first of all, we're going to have a recap on refraction. Refraction is the change in direction of a wave. This wave can include light, sound, any type of wave. For refraction, the angle of incidence is not equal to the angle of refraction. So theta I is not equal to theta R. So imagine we have a perspex block and we draw a normal at a right angle to it. We have a ray of light coming in, which would be your incident ray, at an angle theta I. You have two mediums here, air and the perspex block. The perspex block is obviously denser than air, so it causes the light to change direction and bend, which creates an angle theta R, the angle of refraction. You can clearly see that the light should have gone straight on in the dotted direction, however it is bent towards the normal. Therefore, any time that light travels or a wave travels from less dense to more dense, it bends towards the normal. So if it's going from less dense to more dense, theta R is less than theta I. However, if the light ray is going from more dense to less dense, it is the opposite, so theta R is greater than theta I. That value would be greater. Right, just another two more things to take note of. The denser the material is, the speed of light decreases. However, the frequency remains the same, but the wavelength changes. So, this brings us to Snell's Law. Snell's Law is a law stating that the ratio of the sines of an angles of incident and refraction of a wave are constant between two given media. So this can be wrote as n2 over n1 equals sine of theta I over sine of theta R, where n1 is equal to 1. Don't worry about this formula just yet, as we're going to look at this formula first of all, where n is equal to v1 over v2. N is the refractive index in both formulas, and this represents the ratio. And there is no unit because it's a ratio. So here we're going to look at v1 and v2, which is two different speeds for light. So we'll start with this formula. N is equal to v1 over v2, where n again is the refractive index, v1 is the speed of light in a vacuum usually considered if not given otherwise, and you need to know this value of 3 by 10 to the power of 8 meters per second to the minus 1. v2 is the speed of light in medium 2. So let's put this into an example. Question 1. Light travels at a speed of 1.24 by 10 to the power 8 meters per second in a diamond. Calculate the refractive index. So here you have been given the speed of light in the medium. We'll have a little look at that. So v2 is the speed of light in medium 2, which is the diamond, which we now know to be 1.24 by 8 meters per second to the minus 1. We have not been really given anything about v1, but we can assume that it's the speed of light in a vacuum. So that is 3 by 10 to the power of 8 meters per second to the minus 1. Then you just need to submit these into your formula to calculate n, the refractive index. So v1 divided by v2, and that'll give you the refractive index of a diamond, which is 2.42. Okay. So we'll have a little bit of a more complex question. This time, light passes from air into glass with a refractive index of 1.52 at an angle of 55 degrees. What is the angle of refraction? So this time we'll need to use the second formula, n2 over n1 equals sine of theta I over sine of theta R. This is similar to the formula that I've given you in class previously, where n is equal to sine of theta I over sine of theta R. In the question, we are not given anything about N1, the refractive index of it. But we need to know that when we're talking about air, the refractive index of air is 1. N2 is the refractive index of the glass, which we are given as 1.52. So a reminder, you will need to know that the refractive index of air is 1. You'll have to learn that off. Theta I is 55, but theta R we are not given. So this is what we're trying to find out, the angle of refraction. For this formula, it'd be easier if we rearrange it into the following. So N1 sine of theta I equals N2 sine of theta R. We're going to rearrange it again to try and get sine of theta R by itself. So N1 over sine of theta I over N2 equals sine of theta R. We submit in our values, and we now get 0.54 is equal to sine of theta R. This is not theta R by itself. So to try and get theta R by itself, we have to sine inverse the opposite side. To do that on your calculator, you need to press Shift Sine. And that will allow us to calculate theta R to 33 degrees.